So we have just seen what an isoelectric point is. It is the pH when the cation and anion concentration are equal and no net migration towards any electrode occurs. Now, coming on to how it is useful for us. So let us take one amino acid, for example. We take NH2, CH, R, and we have got COOH. So this is an amino acid containing both NH2 and the COOH group. Now what happens is, suppose I've been given that Ka1 is equal to 10 to the power minus 7, and the other information provided to us is that Ka2 is equals to 10 to the power minus 9. And we have to find, so we find out the Pi, and now Pi is equal to pKa1 plus pKa2 whole upon 2, as we have already seen. And now in these two particular equations that was given, so we can find out pKa1 with the help of them as well as pKa2. So pK1 is nothing but minus log of Ka1, and it turns out to be 7, and this turns out to be 9. So we have got our two values, and if we substitute them, we get 7 plus 9 upon 2, that is 8. So 8 is our Pi. Now what is the use of this 8? Suppose we have this line, this number line, and on one extreme, this is the pH line. So on two extremes, we have the extreme pHs that can exist. So our 8 over here that we just got lies somewhere around this point. Let us mark it. So it lies somewhere around this point. Okay. So we have got our 8 over here. Now, what happens is any pH which is less than 8. So any pH which lies along this particular line. So pH less than 8. What happens is that here the cation concentration becomes more than the anion concentration. Okay, and when the pH is greater than 8, so any condition which lies along this line, so we have over here pH greater than 8. So in this condition what happens is that the concentration of anion becomes greater than the concentration of cation. Okay, and what happens is now, okay, so we know the isoelectric point is being provided to us and we have found it out. So on this particular pH, that is the 8 pH, what happens is we are very well aware that when pH is equals to 8, then isoelectric point exists and the concentration of cation becomes equal to the concentration of anion. So this is how the isoelectric point comes into play when we have to see the concentration of cation or anion which is greater than the other. So let us now just see an example. Now we're considering, let us just see acidic amino acids. Now what happens is we are going to find out the relationship between the various anion and cation concentration. So we have got an acidic amino acid, and let us take an example of it, an hypothetical example. So NH2 acidic means there are more number of COOH group, as you have already learned in the classification on the basis of functional groups. So we have got more number of COOH, and let us assume that this is our given acidic amino acid. Now this is acidic. Why? Because the COOH group, I can see two of them, and the NH2 group is one in number. So this exists as an acidic amino acid. Now what happens is at low pH, so we'll talk about low pH. So at low pH, what happens is that we know that low pH means the solution is acidic, and acidic solution means H plus concentration is high. So there will be a lot of protons, and thus the NH2 will gain a proton and convert into H3 positive, NH3 positive. The rest of the amino acid cannot gain any H positive in any other place. So we have got this particular species coming into play. Now, as the pH goes on increasing, so as the pH goes on increasing, what happens is deprotonation starts occurring. Now, when deprotonations occur, so we have got ourselves a cation at the beginning, and now as the pH increases, this particular cation will lose a proton, and since it has two number of COH, it can lose its H plus from any of this COH. So let us suppose that this H plus is lost from this position and we have got an H positive over here. We'll consider this dissociation constant of this particular reaction as Ka1. Now, this Ka1, when this comes, we have now achieved. Let us look at the species which we just got, and we observe that it has both the positive and the negative charge. So it is a dipolar ion. So we can call it a dipolar ion. A dipolar ion. Okay. Now, moving on, this dipolar ion, in the second step, what happens is that this particular dipolar ion will now lose a proton again. So let us just see this reaction also. So we have got ourselves a dipolar ion having both the positive and the negative charges. So it looks something like this. Now, with time, the H plus is again occurring. The H plus is again being lost. That is, deprotonation is being occurring again. And when this happens, this NH3, the H positive remains intact in this one, but so the more acidic H are at the COOH, and since we have got one more COH to the rescue, this COOH will lose its H plus, and this H plus comes into this deprotonated ion structure. Now we have got Ka2, that is the dissociation constant, the second one. So now what we saw is that we have got ourselves a new species, and in this particular species the negative charges are more than the positive charge, and thus we can call this particular species as a anion. So now we have got ourselves an anion, and this anion came from a dipolar ion which we had previously. So dipolar ion goes to deprotonate itself and convert into an anion and giving us a dissociation constant as Ka2. Now what happens is that again this anion, so let us just take this anion in the third step, we observe that we take this anion again, so we have got NH3 with a positive charge and we have got CH2, CH, and these both the COH have lost their H positive, and now we are only left with the H of NH3 positive, and thus in the next step this NH3 will also lose its H positive and convert into NH2, and we get this particular structure. Now here also an H positive is taken out, and now what we get, the dissociation constant is called Ka3, and it is the third dissociation constant. So we had to find the isoelectric point. Now what was the isoelectric point? The isoelectric point is defined as the pH when what happens, the cation concentration becomes equal to the anion. Okay. Now here the last species that we received, that is this particular species which has two negative charges and no positive charges. This is a dianion, as we can clearly see, two negative charges, and this is a dianion. So now in the isoelectric point, when we are considering the isoelectric point, we have to see that the cation and the anion have equal concentration, but here we have a dianion. So now, please, we have to keep this in mind that dianion, the presence of dianion doesn't concern us because we are only concerned till this portion. Which portion? We're only concerned till we get a cation and we achieve an anion. So till here, this Ka1 and Ka2 is of importance to us, and the Pi, that is, we have to find if the isoelectric point we have to find, then the isoelectric point will be from the contribution of this particular Ka1 and this particular Ka2. So if we are going to write the isoelectric point, let us just write the isoelectric point and see for ourselves. So isoelectric point, which is represented by Pi, will be equal to half getting contribution from pKa1 as well as pKa2. So this is the isoelectric point, which is getting contribution from the cation and the anion, and the dianion is not concerning this particular Pi. Now, if we draw this, so we are going to show the pH line again. So at two extremes, we are aware that we have got 0 and 14 at the two extremes. Now we have got the Pi, say the Pi is over here. So now if the Pi is over here, this particular Pi, we know that this is equal to, so at this particular point, we have half pKa1 and pKa2. Okay, so we have got this over here. Now, any concentration which comes below this Pi, that is over in this particular place, so any concentration over here will have the cation concentration greater than its anion concentration. This we are aware of, and this is the isoelectric point. So mark it as I here. Now, what happens is that any concentration which lies on the right hand side, that is above this isoelectric point, automatically the anion concentration becomes greater than the cation concentration, because at Pi the cation and the anion concentration are supposed to be equal. So this is the pH line. Now if we have to find out that, suppose we have to find out the second Pi that we got. So that second Pi that we obtain will be from, it will be half pKa2 and pKa3. So it will be from the contribution of pKa2 and pKa3, and this is the second I that we are getting. And over here in this particular isoelectric point, the anion concentration, so over here the cation concentration is equal to the concentration of dianion. As we have seen that in pKa3, that is the dissociation constant third, there is a formation of a dianion. So here cation will be equal to the dianion. Okay, and any concentration which lies above this, so any pH which will lie on the right hand side, on this particular side, let us mark this. So any concentration lying on here will show that the concentration of dianion will be greater than that of the anion. Okay, so this is the pH scale that we got when we see any acidic amino acid, and this is what we obtain. So the dianion doesn't matter to us as long as we are concerned about the isoelectric point, as we have seen. And at the second point, that is when the cation becomes equal to the dianion, we can see that we have got another isoelectric point, but that doesn't matter, because see, this is actually not an isoelectric point, because isoelectric point is cation is equal to anion concentration, and here cation is equal to dianion. So we use the formula, but this is not as such an isoelectric point, because isoelectric point, the main definition is when the pH, it is the pH when the cation and the anion concentration becomes equal and no net migration occurs towards any electrode. So here we have achieved when we have got an acidic amino acid, the sequence of the Ka, that is the dissociation constant, as well as the concentration of cation and anion on a pH scale.